Many of you will have seen water drawn like this. You will likely never have seen it drawn like this because it's a terrible diagram, but it's going to show you exactly what I want it to. If you were these electrons in this bonding pair, in this covalent bond, either of them, you would probably more likely end up sitting closer to the oxygen, which is here, than the hydrogen, which is here, given that the hydrogen atom only has one proton, whereas the oxygen atom has 8. Therefore, actually what ends up happening is these electrons tend to move that way in both of these bonds. And what ends up happening as a result of that is this molecule, this water molecule, starts to develop unequal charge from either end of it. Because these electrons are sort of displaced and they're sort of shoved over towards the oxygen itself becomes slightly negative. The delta just means slightly, that's a lowercase delta, for those of you who haven't done Greek. Okay, so it's a lowercase delta. And this property, this polarity of water, is what gives it a lot of its interesting and also important properties. So this is what it will sometimes be drawn like, and I'm just showing you the electrons in this bond. It's very common for water to be drawn just like so. Sometimes they won't even give you the charges, they'll just assume you know them. And let's have a look at actually what's so clever about water. So hopefully if you start to just think about actually how water may interact with one another when in a solution, you'll start to be thinking maybe the positive bit and the negative bit can form some sort of weird intermolecular force with each other. And therefore water will stick to each other and just start to link some of these ideas that you know. The problem is, actually, as I've said here, it's not just a negative positive interaction in terms of the one positive end of a water molecule forming an interaction with a negative end of another. They have a special type of bonding that can occur known as hydrogen bonding, which you've had there. And what this is when you have the lone pair, so this is going to a chemistry basis, you don't really need to know it for biology, you need to know that hydrogen bonds do form, but if you understand it, it will help in basically every other part of biology. In oxygen, you have two pairs that aren't involved in the bonding on that external shell, that outermost shell, and these are known as lone pairs. And on this water molecule over here, you have a hydrogen atom that's electrons are actually getting pretty far away from it. So you have this sort of positive charge here, so this very delocalized hydrogen atom, as it's known, and you've got a pair of electrons that aren't forming a bond, and hopefully you can start to sort of see that maybe, just maybe, if close enough and at the right angle, those doing chemistry will know that angle is 180 degrees, okay, if at the right angle as well, actually you can start to form this weird bond where this hydrogen actually starts to sort of literally form a bond with the lone pair of the oxygen. And these hydrogen bonds, compared to any of the intermolecular forces you've learned about, are pretty strong. And that's what gives us so many of these brilliant, wonderful properties of water. To take through hydrogen bonding really quickly, it can happen with anything where you've got an atom that is electronegative, so all that means that it's good at dragging electrons away. So nitrogen, oxygen and fluorine are usually pretty good at doing it. There are others, but let's just have a look at these and see whether, so just to reiterate my point and actually get you used to seeing where hydrogen bonds could form, hydrogen bonds could form here between two ammonia. So this is ammonia, this is what ammonia looks like in terms of its shape, but again you've got hydrogen which is getting a little bit delocalized, so it's electrons heading towards that nitrogen because nitrogen's really good at dragging electrons away from a bond, and a nitrogen has one lone pair, so you can get a hydrogen bond forming between two ammonias. Equally, you can get a hydrogen bond forming between ammonia and water. It doesn't always have to be the same thing. So here we will have a hydrogen bond forming like so. And that's all you really need to know. The idea that actually if you see a hydrogen that's attached to something that's electronegative, that's good at taking away the electrons, which in biology will be a nitrogen or an oxygen, you'll get hydrogen bond formation. Over here, fluorines, just to prove that it doesn't always, it's not just looking for those elements. Here you have fluorine, and fluorine's really good at pulling away, good at pulling away electrons, like so. So they'll all be delta negative. But actually, when you've got loads of fluorines, you don't have any hydrogens, so you can't form any hydrogen bonds. So you can't form hydrogen bonds here. That doesn't work. If I brought in, for example, a water, and fluorine does have some lone pairs, I can't remember how many, and Mr. Sherm, if he ever sees this video, will shout at me. But if I then said, let's get some water around here, water and its hydrogen, which is delta plus, that delocalized hydrogen, because the electrons are all the way over here, can again form a hydrogen bond here. So that's hydrogen bonding. One last thing to talk about, it can even happen between molecules. So this is one big old molecule. That is our molecule all around here. I've drawn this. This is actually what protein looks like. And I just thought it interesting to point out to you that actually you could get hydrogen bonds forming within a molecule. You've got an oxygen over here, and a hydrogen over here. You've got a nitrogen over here, and a hydrogen over here. Just do it in different colours so you can see. And you've got an oxygen here and a hydrogen here. So actually you can even get hydrogen bonds forming between within a molecule itself. And this is actually really important in protein structure. So those of you who know that will sort of be going, hopefully. Now, one of the reasons this is so important is because all these different things hydrogen bonding to each other means that actually when water is a liquid, when these molecules are all here, actually there's pretty strong interactions occurring between all of them, which means to change from one state to another, to get these molecules to increase their distance from one another so much so that they turn into a gas, or if they're a solid turn into a liquid, takes a lot of energy. And this is known on a macroscopic level in terms of just like needing to heat it up to get it to change state, which means it has a high boiling point. Okay, to put that into comparison, if you look at nitrogen, which is similarly just a similar size molecule, I know it's only 2 atoms, but nitrogen isn't polar. Okay, the electrons in here are going to be in the dead center of this molecule, and it doesn't form hydrogen bonds. Actually, you start to realize how strong those hydrogen bonds are. It's actually, so the boiling point of nitrogen is minus 200. And what I think is quite nice, just to give you an example of before, because ammonia, which is a gas at room temperature, has some hydrogen bonding, it's sort of in the middle. So water can form lots of hydrogen bonds, ammonia less so, and you can see that reflected in their boiling point. This idea of not wanting to change state particularly well of water is actually quite well exemplified by sort of looking at sea temperatures versus outside air temperatures. This is the minimum and maximum temperatures in January over the course of a day in Folkestone, just because it's the only place I could find any data for. So actually, during the day, air will change a lot. Air does not have a particularly high heat capacity. So it doesn't take a lot of energy to change, or changes in energy to change its temperature. Whereas water stays pretty constant, and that's what you want biologically. We are talking about biology, not just water. I promise there's a lot of chemistry in here, but this is where we're talking about actually the properties of water. Water doesn't change temperature particularly quickly, which means it gives you a stable environment, and organisms enjoy a stable environment. So water gives you a thermally stable environment. It will change temperature throughout the year, but it doesn't change anywhere near as much as it would during the day. So it's a nice stable environment. The reason is because of those hydrogen bonds. It takes a lot of energy to get them to not only heat up but also change state. Humans mostly will use this to their advantage as well. So actually the fact that it needs a lot of energy to change water into a gas means that if we put it onto our skin and allow it to evaporate, the evaporation and the latent heat of vaporization, as it is known, water has a very high latent heat vaporization, meaning the amount of energy needed to change it from a liquid to a gas, which we exploit in sweating, because that energy comes from our body heat, which dissipates our body heat. If we are putting energy into evaporating water, that heat energy is no longer in our body and it cools us down. A use and a property of water. So it's got a high boiling point, high melting point, it's got a high latent heat of vaporization. Those things are fairly similar to one another. One other thing that it also has is it tends to stick together. So water tends to be quite sticky to itself. Actually, if I were to put my finger in here and drag the water along, it would, you all know it does that thing where it sort of spreads out. Water follows itself, again just due to the hydrogen bonding and its polarity. It forms quite good interactions with itself. This is also what gives rise to those lovely rolled edges of surface tension, so you can actually pile quite a lot of water on top of itself. And the reason is, actually, if you look at, so this is meant to represent a penny, and you can put quite a lot of water onto a penny. Actually, what is happening here, this water should fall off with gravity, but it's not, because it's sort of held in a mesh by hydrogen bonding with lots of water molecules further in. This is known as surface tension. And surface tension is a strange one that they want you to know, because it's not important for many organisms, but surface tension also occurs on sort of flat lakes and things, and these molecules have bonds between them, so you weirdly get almost a solid structure forming at the surface. And some animals, such as pond skaters or water boatmen, can actually use that surface tension to walk on water in an almost biblical fashion. Okay, so that is one of the properties of water, is that it creates surface tension at an air-water interface, and occasionally animals and plants can use that to their advantage. So not the most important, but it's still there. The fact that it sticks to itself is important in transpiration, which you'll learn about further down lower sixth, but water sticks to itself and other things quite well, which is actually used in transpiration. If you think of transpiration, I put a leaf up here. Transpiration works by water leaving the leaf as water vapor up here, but actually dragging water, this water molecule leaving here, because this one sticks to it and this one sticks to it. As this one leaves, this one follows. So the cohesive action of water, the fact that it sticks to itself, is very important, but also it is adhesive as well, meaning it can sort of stick to the wall and crawl up the wall of the xylem itself, which I think is probably what's being shown here. Again, you'll learn far more about this when you do plant transport later in the year, but something that could come up in a water question, saying what's the difference between cohesion and adhesion. Cohesion is water sticking to itself, and adhesion is it sticking to other things, which is very useful in transpiration. One of the most important things about water, and one of the most important things in life about water, is that it is very good at dissolving stuff. It is a good solvent. It is a good solvent. And what you can do with that, and the reason that water is such a good solvent is because it can form interactions with lots of things. The chemists amongst you will know that that things dissolving is a result of the solvent forming interactions with the solute. So let's take some examples of stuff that you know dissolves in water. So I've got glucose here for those of you who don't know, alpha glucose to be certain, and you can see that actually all those OH groups that stick off the water can form hydrogen bonds. And as I just said, the thing that determines whether something dissolves in water or not is whether it can form interactions, and hydrogen bonds are a very strong interaction. The stronger the interaction, the more likely it is to be soluble. And because water can form so many hydrogen bonds with glucose, it dissolves. And that's really useful for when you're wanting to transport, I don't know, glucose around your body in the form of blood. It's a lot easier to transport it when it's dissolved in the water and sort of trying to throw it around your body like sand. Equally, let's take something else that you know about. Amino acids, they're in your blood as well. And how come they can be transported in your blood? Because they have lots of little groups that can cause it to dissolve in water. It's got this carboxylic acid group, so this CO, as we said earlier, O, can form a hydrogen bond with water like so. You've got an OH group that I've just shown you can do it. You've got an NH group that can also do it, which I've showed you earlier with ammonia. And you've got another two down here. So again, it's a good solvent for amino acids. And finally, you've got salt. And salt can't form hydrogen bonds. These are charged molecules, charged ions by nature, and they don't have any hydrogen. So how do you sort of dissolve these things? And the answer is you can still just form interactions with them. All you need to do is form interactions, and there's no name for these interactions. It's known as the formation of hydration shells for the chemists amongst you. But again, you don't need to know this; you need to understand it. Actually, sodium ions can dissolve in water, and chloride ions as well, because actually the negative end of water can sort of just form a little electrostatic interaction here, and between the negative oxygen. And chloride can do the same with the positive hydrogen. And again, you could get bond formation, and therefore stuff dissolves. And that's why water is such a good solvent for sort of charged and polar molecules. You'll learn more about that in membranes, but again, something to know, something to understand. The final thing, which again is mildly irrelevant, but you need to know it, is actually that water, when in its solid form, floats. And a lot of people roll their eyes, like, obviously ice floats on water. I've had a drink before, but actually it shouldn't. And you are under a misconception because you've seen so much ice in water, and I can show that to you very clearly in terms of density. So actually, if we take anything else and we think about it, let's say I've given you 100 molecules of something else, and then say to you, right, those 100 molecules, how much volume are they going to take up if they are a gas, liquid, and a solid? You'll almost certainly say the gas will take up the most volume, unless it's incredibly highly pressurized, but we're not going to talk about that right now. Then a liquid will be the next, and then a solid will have the smallest volume. And if you look at your actual, this is density, this is mass, so just stuff, and this is volume. Your volume for your solid should be the lowest. Therefore, your density would be the highest. So if I were to put a solid in a liquid, the solid should sink because it's more dense than the liquid. And that doesn't happen with water, and that's weird. And that's a special property of water. And again, it comes down to its hydrogen bonding. You've seen water floating. It's important for polar animals. It gives them a habitat to walk on, but also for sort of fish and other animals in the water beneath, it acts as an insulator and keep heat in, so you have a warm environment beneath. If it was stuck to the bottom of the ocean, you wouldn't have that. So the reason it does that, you don't need to know this again, is because of the hydrogen bonding, it sort of forms this six-membered lattice structure. And you do know this already, because if you squint at this photo, it looks like a snowflake, and that's why snowflakes are the shape they are, because of the hydrogen bonding of water when it freezes. But the important bit here is that this solid has a high volume, and because of this lattice that it forms, the solid has lots of gaps in it, so it actually forms a high volume solid, which is actually less dense than its liquid counterpart. That is very strange. In terms of notes you need to know, I've written these things here. This might be worth pausing and screenshotting, but this is what we've spoken about today. These are the examples you need to know, so please go away and learn them.